So welcome everyone. Today we have Matthew Yu from Perimeter, and he will tell us about gauging non-invertible surface operators. So go ahead, Matthew.
Great. Hopefully everyone can hear me okay. So yeah, I'm going to be presenting today on some work that I recently did with my excellent collaborator, Thibault Decoppet, that came out last month. And oops, sorry. So let me go over kind of the outline for this talk. I'll start with some motivations for this work, how we got started, both physical and from the mathematical point of view, why we were interested in doing what we were doing. Then I'll give a brief review of kind of topological theories in general and how we think about topological theories in this work, and also the categories that are related to these topological theories. So I'll give you kind of another review of basic properties of two categories, namely the ones that are important for us are the braided, syleptic, asymmetric two categories. Then I'll also introduce to you this notion of something called like a strongly fusion category, which is important for many of the calculations that we're doing in this work. Then I'll move on to the main theorems about condensing in two categories. And well, these theorems may seem a little bit difficult, but hopefully I'll kind of also include some examples so that everybody can understand what these theorems are really saying. Then I'll present some cohomology computations for the braided strongly fusion two categories. And at the end, where I'm going to show kind of a nice wrap up to this work, which is basically proving something called the two-Deligne theorem, which really tackles the symmetric strongly fusion two category case. So the motivations for this work, okay, well, we were kind of thinking about this idea of no global symmetries in quantum gravity. And not only should there be no global symmetries, but the lore goes that there should be no global categorical symmetries as well. Therefore, there should be no anomalies for the symmetries or the categorical symmetries, i.e. the non-invertible symmetries that one can possibly have in kind of the topological sectors of some quantum gravity theory. So in the context of gravity, this means that basically, this topological part, which is in general described by some even higher category, should be kind of completely condensable to the vacuum. So what we wanted to do was we took this motivation. We want to say, like, let's generalize the notion of an anomaly for an actual symmetry to an anomaly for an invertible symmetry. And we kind of just wanted to push this idea as far as we can go and see how far the generalizations could actually go. So what I want to kind of start everyone off with is I want everyone to think of kind of the anomaly to be something like the obstruction to a fibre functor. This is not exactly what this is not exactly what the anomaly is going to have to be. I'll put a caveat kind of later on in a later slide, but have this kind of idea in mind, right? And think about this in the context of what I just said about quantum gravity. So this fibre functor says that if I have this symmetric K rep G is some group, higher group, whatever you want to whatever you want to call it. Then there's a functor from this symmetric category into K vector spaces. So for this talk, I'm not going to worry about too high of the categories. Mainly, we're just going to stick with two categories, and I'll consider basically fibre functors in this series. In this theory. So you can think of this as kind of maybe a baby version of the full story of all the topological operators that can exist in some higher dimensional theories. But now we just do as much as we can with kind of the surface and the line operators. So if the category is fully symmetric and fermionic, let me just say that this fermionic part is going to be important for us. We can upgrade this fibre functor from this two category, which will always be denoted by some math frac. And there's this fibre functor that maps it basically to 2s vec. So we're going to think of it in this way, at least in the fermionic case. Now, for a physical theory, like actual physical theories, I want to say that kind of the primary operators in the category of all operators, they must all be detectable by some other operator in like the category. This kind of goes by the notion of remote detectability, which I'll review a little bit more later on in the talk. So we don't want something like a full fiber functor always. And in fact, we generally won't have a full fiber functor because our category is not going to be symmetric. We generally want some, some notion of objects being detectable. So this is not the entire story that we're going to work with, at least for the theories that we talk about. But I will talk about this symmetric case at the end of the talk when we go to the Deligne theorem. So this is kind of just a bit of an appetizer, but okay, let me kind of summarize the questions that we're going to try to answer. So consider some fusion two categories with some level of monoidality, right? So braided syleptic or something like that. And we want to ask, what are the structures of these two categories that you can tame by condensing some sort of suitable algebra object inside of this category, right? Like what happens to the ambient structure of C if we can condense there? And in the cases when we can condense to the vacuum, what are the, what possible obstructions can there be to maybe you condensing to the vacuum or you being able to actually go all the way to the vacuum? So this kind of goes in line with this anomaly thing where it's kind of like, okay, so certainly if a category can be fully condensed to the vacuum, then there's no anomalies to talk about, right? There's just no topological operators for the invertible things, and there's no topological operators for the non-invertible things at all. It's just the category is basically just fully empty. So if in the cases where there is some obstruction to condensing to the vacuum, so maybe you have some lingering kind of surface operators lying around, it's still, so this is the part that we didn't fully flesh out, and we don't know how to actually do this, but we're not sure how to actually define the anomaly in that case where we really just have kind of floating or like, remaining topological operators, objects, let's say objects in the two category that are non-invertible. So we don't know how to compute something like associated to an anomaly there. I have some ideas that we can kind of discuss later on, but let me just say that this is not going to be fully defined in this talk. So, okay, so much for the motivations. Let me discuss a little bit about kind of, well, the phases of matter and things that we care about. So a class of phases that can appear, of course, gap phases. And in particular, so the ones that are really nice and that are like really computable in some sense are the invertible phases. Sorry. So the space of n-dimensional gap phases gives this thing called an omega spectrum. It's the algebraic topologist version of kind of an abelian group. And the point is that, this is really the world in which kind of actual anomalies live for actual symmetries. And it's very computable. We have very good ways of computing these objects. You can compute kind of the cohomology associated to some group like symmetry. But then, there's also these non-invertible phases. And when I say these non-invertible phases, I really want you to think of like a full topological field theory, topological order. And this phase is not just determined by its symmetry. It's some more non-trivial kind of extended objects in different dimensions. And the structure of their interaction is captured by basically, category theory or higher category theory. So there's two things to really think about, right? We can kind of talk about categories, purely just from a mathematical standpoint. But at some point, at some point in this talk, it's going to be important to kind of differentiate between classifying the categories and really saying, okay, there's some theory associated to this category. And then we compute some things associated to the theory, which is kind of modeled by the category. And these non-invertible phases are really going to be the type of phases that I want to focus on for the remainder of this talk. Okay, so more about these topological order phases. Let me give you some properties, which is that, okay, of course, there are extended operators and kind of mediated by like kind of long range entanglement, which is maybe what the condensed matter physicists want to say how these things kind of emerge. And the phase is basically locally trivial, i.e., there's no non-trivial local operators like in the d bar that could have perturbed us away from this topological phase. So essentially, basically, all the UV operators are gapped out, and the local phase in the local physics is really invariant under diffeomorphisms, becomes totally topological. So these extended operators are in general supported on line surfaces or some higher dimensional operator or some higher dimensional surfaces. And there's another thing you can do, which is you can build higher dimensional surfaces from lower dimensional ones. This is the idea of condensation. So, essentially, you can kind of condense a symmetry, you can condense a non-invertible symmetry, or some people like to call this gauging. And in particular, what this means is that you can think of it in kind of a physical setting, which is like you start with some phase, say like the empty phase, which is the vacuum, and then you flood it with a network of interfaces, and then you build the phase kind of upwards from there. And what's going to be important for us, and also important in kind of the classification of topological theories in general, is that we'll say that two faces are equivalent if we can build a gapped interface between them via some condensation procedure, i.e., we call two kind of phases equivalent if they're like Morita equivalents, separated by some gapped interface. Now, this is a good classification in kind of the topological world, but I mean, this is not the only classification that exists for like all theories at all. So maybe, if you wanted to study other types of classifications of other things, you maybe separated by some sort of gapped interface is too coarse of an equivalence principle. So okay, so before I go too much into the two categories, is there any maybe I should stop quickly for some questions if there are any. Okay, so great. So let me discuss a couple of axioms associated to this two category. And these axioms really, come because they're all really like physically motivated. So first, we want something that's kind of linear, additive, and Karoubi complete, meaning that so Karoubi completion is kind of like saying that all objects that you have that you could have gotten from condensation also exist in the category as well. We also want kind of a notion of rigidity and finite simplicity. And these are the properties that are going to, are associated to something that's like very topological. So it's kind of like the nice finiteness properties that allows your theory to feel very topological. And then we also want a trivial center. So the only invisible operator are scalar multiples of the identity. And this trivial center goes back to what I said kind of in the beginning about the detectability, is that we don't want kind of objects that are just invisible in the category, not detected by any other object. And finally, the only point operators are scalar multiples of the identity, so we don't have any non-trivial two morphisms in this category. Basically saying that if you had kind of non-trivial operators or like non-trivial point-like operators, that could potentially deform you away from this topological phase, and also complicates our things. Also complicates our calculations a little bit. So let's just assume that the only point operators are scalar multiples of the identity. Okay, so now I want to include more levels of monoidality into this two category. This is what we were saying. So let's start off with a braided monoidal two category. It comes equipped with a braiding, which we'll call B. This gives you an equivalence between a product of two objects, AB to BA. And then there are two invertible modifications called R and S, which is some sort of coherence. And they satisfy certain relations in this two category, which I'm not going to spell out in full detail. But anyways, this is one of the structures that we're going to be considering for this talk. So we can equip a braided monoidal two category with an additional structure called a solipsis. The solipsis, you can see from this diagram, kind of takes us between a braiding and the opposite braiding in this way. And of course, it also satisfies certain relations, which I don't need to spell out, but just so that you know what the solipsis actually does in terms of the braiding. What we can do is you can also take this a step further, is you can define a symmetric two category as one where solipsis satisfies the following property. Basically, this equation is satisfied between the solipsis and the braiding. So really, it's an additional structure on top of this, or it's an additional condition kind of on top of this, on top of already being selectic.
So should I think of this two categories describing surface operators in a 6-dimensional theory?
Exactly. Good. So if you right. So in the fully symmetric case, you want your kind of surfaces to really have all the as much freedom to move as you want, and the natural setting for that is in 6 dimensions. I'll go over the counting a little bit more, but yes, that's correct.
But throughout this talk, we are assuming symmetricity, right?
Sorry,
Or no?
I didn't hear.
Throughout this talk, are we assuming symmetricity? The
No,
symmetric structure.
we're not going to be assuming the fully symmetric setting, right? Right. That's the point in the beginning, is that like I don't want to work in the fully symmetric setting. I'm just throwing this out here because at the end we're going to talk about symmetric two categories.
Thanks.
But in general, we're just going to in general, I'm going to prove to you theorems about syleptic and braided stuff. There you only need kind of 4 and 5 dimensions basically.
Okay.
And,
thank you.
I'll make sure that the dimensions are clear to people, and if not, please ask. Yeah, thanks for the question. So just to give you maybe a little bit more physical interpretation of being syleptic. So given surfaces in 3 ambient dimensions, then to braid them means kind of passing them around each other in a 2-parameter family. So you can imagine that these surfaces go around each other topologically as basically like tracing out some sort of a 2-sphere. Now, this procedure results in a phase factor that depends antisymmetrically on the inputs, i.e. there's some pairing that pairs 2 objects, A, B, and it's antisymmetric with respect to the inputs. And it's interesting, the fact that kind of these surfaces trace out this 2-sphere. You could contrast this to the braiding of lines, say in Chern-Simons, when you have 2 ambient dimensions. This operation is fully symmetric, right? And the braiding happens, kind of the lines pass around each other in basically like a 1-parameter family, which is they kind of just pass around each other in a circle. So this is kind of a nice, I don't know, maybe this is helpful in terms of how to visualize things and why kind of maybe something antisymmetric is associated to the solipsis. So, but the point is that kind of when you braid 2 surfaces, since you have this ambient dimension, what you can do is that at 2 locations, the surfaces can basically switch places with each other, kind of which one's on top and which one's like below each other, by going into the 5th dimension, kind of using the solipsis. So basically, if you're in 4 dimensions, the problem is that the surface will kind of get like knotted up or kind of linked. But then in 5 dimensions, you have this extra freedom of using the solipsis to basically like turn them around. Okay. So now we have some, general knowledge of 2 categories. I want to specify to a very important type of fusion 2 category, and this is something that was done with Theo a year or so back, which is this notion of something called a strongly fusion 2 category. So suppose we had done the following. Suppose you took your 2 category which had surfaces and lines, and we condensed to a phase with no lines. So basically, the lines was just basically SVEC. There are no non-trivial line operators. It still has kind of non-trivial surface operators, which form this kind of this fusion 2 category. But we'll call these categories strongly superfusion, or super in the fermionic case. And now an important property of these categories that have no lines is that basically the equivalence classes of the indecomposable objects form a finite group. So this is very nice. It's like saying that in this very specialized case, the multiplication of these surface operators really behaves like a group. I.e., you could think of it, or better stated, kind of a simple times a simple gives you like another simple, rather than in general you can imagine that there are fusion coefficients and things like that. You could spit out linear combinations of different things, but here it's not the case when we don't have lines anymore. So for the rest of the talk, at least for the most important parts of the talk, let's just say that the fusion rule is going to be described by some finite group. I'll call it E. In particular, the E is going to be abelian for a lot of the things that we care about. And okay, so we're going to use strongly fusion in conjunction with some other facts about kind of how many ambient dimensions we have, right? This is going back to kind of Lakshya's question, which is that, we need to consider this two category in some setting, in some background setting. And given some background setting with some ambient dimensions, we can put on some extra monodality conditions into our category. So this at the end, or these two ingredients will basically kind of lead us to the cohomology computations that we're going to do towards the end of the talk. Okay, so before I state kind of the theorems, are there any more questions? Okay, great. So so assigning some extra properties to our category, we can prove basically the following theorems. And let me just say to begin with, like, you don't have to follow the details of all the theorems, but essentially what's going to happen is I'm going to go kind of braided, syleptic, and then you're going to see kind of the properties of the properties of each of the theorem are kind of like analogous to each other. So let's start off in the braided case. So if you start off with a braided, say, multi-fusion 2 category, you consider a braided separable algebra inside this B. You could consider mod, or the modules of the algebra inside this category, and this forms a multi-fusion 2 category. So notice that we lose the braiding in this case. Let me give you an example right away of this, which is that, okay, take this B, oops, I guess this should be non-curly B, to be a braided multi-fusion 1 category. So then you can take basically, you could take the modules of this multi-fusion 1 category with respect to 2vec, and then the result is basically a multi-fusion 2 category of finite semi-simple right B modules to this thing. But you don't have the braided structure. So let me say another thing, which is that for something that's syleptic, so notice what happens in the syleptic case. If we start off with a Karoubi complete syleptic monoidal 2 category, and you consider some symmetric separable algebra inside here, you could take the modules with respect to this guy, and then this is going to be a braided monoidal 2 category. So notice that we've kind of stepped down this monoidalness in our initial category by taking modules kind of away for this category to n. It's still a 2 category, but it just loses one level of the monoidality. And okay, to go a little bit further, let me introduce the definition of a symmetric center of mathfrak S, so denoted as the following object. So it is the full sub2 category of objects in C, such that basically these objects commute with all the other objects like D inside of.
Sorry. What is the Z sub 3? It's a little fast.
Sorry. The symmetric center of this one I denoted by Z sub 3. It's called the symmetric center of this category. Okay. It's basically it's basically just the sub2 category of all objects that kind of are symmetric with respect to everything else.
Okay.
All the other Ds inside the category. Yeah. So, okay, given this definition, we can say something more about this. So suppose that, so take the same conditions as in the first theorem. So suppose it was syleptic. And now suppose this symmetric, so now suppose that B is a symmetric separable algebra actually inside the symmetric center. Then, interestingly enough, you preserve some level of monoidality. So this, the modules with respect to this algebra is actually a syleptic monoidal 2 category. And this is because, I've equipped this with kind of more conditions. So the general idea of all these theorems is kind of, sometimes you lose monodality, sometimes you preserve monodalities, depending on kind of what type of objects you choose to take modules of, i.e., like in some sense, condense. So let me give you a physical picture of kind of what of what my theorems were saying. So essentially what I'm trying to do is you take this category C, right? And essentially we're trying to find some possibly gap boundary of the initial 2 categories C and trigger a condensation maybe all the way to 2vec if possible. So notice the following, what I've been doing is I took some category C. Okay, it wasn't called C before, but it was called, S in mathfrak B. I condensed, some algebra here. I got to basically the modules of this guy. So you can see why kind of in kind of the most vanilla cases, I'd lost some level of monoidality because I kind of collapsed it onto like a boundary. And the point is that, you know, sometimes we get stuck at this module stage, right? Like I only say kind of the modules with respect to some algebra object, you know, it's some sort of 2 category again, which is, okay, maybe not so great, right? It still seems kind of complicated. And the question is really, can we push this further to maybe say, okay, in which cases can I go even further and say something about this 2 category to make this really condensable all the way to 2vec? So now we've kind of, so now like, can we really annihilate like all the possible things in our initial category? And this is when we're going to use some facts about the strongly fusion. So now we're going to expand on the theorems a little bit more and kind of push this a little bit further. So the theorems that I just flashed were kind of very general statements, but now let's try to see if we can go even further. So the idea is, you know, if we could make the resulting category after condensing strongly fusion, then that's great. We can use cohomology to see if we can condense all the way to 2svec. So really the obstruction there becomes something very computable because we have kind of like a group-like structure. Now, the nicest case actually is when you can take your initial category, you go inside the category and you find a sub-2 category that looks like 2repg inside our original category. And the following theorems will kind of expand upon this. So kind of the idea is basically, you know, if you can find this 2repg sitting inside, the idea is to condense something inside this sub-2 category that looks very nice, which looks like 2repg. And basically say, okay, if I could condense inside this subcategory, what happens to the ambient category after I condense here? Maybe some nice reorganization actually happens. And this is indeed what we find. So theorem, consider a braided fusion 2 category. And now suppose we can kind of look inside this category into the identity component and you find 2repg. Okay. Then you could condense this object, which I'll call var phi, which is vecg. And then if you take the modules with respect to this phi, actually, this is very nice, which is that this is not just a 2 category, but actually this becomes a strongly fusion 2 category. So this is really using the fact that I could have looked inside the category and found a 2repg like sitting in the identity component, and then I could condense out this thing. So there are also implications of this last theorem for the seleptic case. So let me just say, so let's take this guy to be a seleptic multifusion 2 category. And let's suppose, again, you can find some inclusion of this 2repg inside this guy. Okay, then this automatically includes to the symmetric center of this object. So namely, this 2repg is necessarily contained inside the identity component of S, just like how I said before. So corollary, if you have this inclusion of 2repg inside S, then actually when you take now kind of the condensation of the same phi from before inside this category, you get a seleptic strongly fusion 2 category. Notice before it was braided, now it's seleptic. And the canonical monoidal 2 functor is also seleptic. Okay, cool. So, this was a statement about kind of finding nice connected things inside your category, like 2repg is connected. And let me give you some examples right away about kind of how this works, so you have more of an intuition. So again, let's consider our ambient category to be this guy. So think of this as kind of the mathfrak B or mathfrak, yeah. Think of this as like the mathfrak B or something. And then take module with respect to sVec inside here. So you find that basically, if I took the modules of sVec with respect to 2repgz, I get basically 2sVec as you know. This is just saying if I take this guy and I condense out sVec, I get 2sVec. And that's because I've really viewed sVec as an algebra inside of 2repgz via this inclusion. So this is kind of the simplest, this is like the simplest case where my ambient category already itself, you could have kind of, it felt very much like 2 rep G with like an extra Z. The Z2 being kind of like this object in like in the center that's order 2. So let's give another example. So let B be a braided fusion 2 category. And okay, so now we have this braided monoidal inclusion of 2 rep G inside B. Assume we have this inclusion. Again, so condense this algebra inside of this thing. And basically you have a strongly fusion 2 category equipped with this monoidal 2 functor from B inside this inside of mod of this algebra with respect to B. So the way you can kind of think about this is as follows, right? Kind of vec G, right? You should really think of kind of as like lines in some sense, right? Vec G you can think of kind of which I'll also repeat a little bit later, somehow like kind of the sum of like the group algebra basically. And then when you condense inside a very nice category, right? It's kind of like you're getting rid of all of these lines in some sense. It's like, and then if I get rid of all these lines, then basically, of course, I'm kind of left with only the surface operators that are left in this theory, and the lines kind of have like all gone away. So that's kind of the intuition that you should take away from this, like these nice categories where I could kind of reach inside and pick a copy of like 2 rep G. But now let me go to the disconnected case. So suppose your fusion 2 category of surface operators and their interactions was given by 2 vec G, right? So again, you can consider the algebra vec G inside 2 vec G, just the sum of the equivalence classes of simple objects. So vec G is again the fusion 1 category of G-graded vector spaces viewed as an algebra inside this. And the point is that I can condense, or I can take the modules I can take the modules of this algebra vec G inside this 2 vec G. And what you'll get is you'll get 2 vec basically. So I basically get rid of all the group structure. I kind of eliminate all the group structure here, and I just get basically the trivial theory. So this is a bosonic example. Okay. But this is a very simple case, right? Where your category was just 2 vec G. Can we do a little bit more, right? So let's play the same game again. But now you go inside your category B, some braided fusion 2 category, and suppose you kind of reach inside and you plucked out, instead of 2 rep G, you plucked out like 2 vec E. E being some abelian group so that I have like a braidedness. And now you could consider basically taking the module with respect to this vec E algebra, because I found a copy of 2 vec E using the lemma from before. And now I could condense this object out, and basically the 2 category I get from condensing is a fusion 2 category. And moreover, what I can do is I can say, okay, let's look at the components of the thing that appears after I condensed out this vec E. What happens is that your original, if you took your original category, right, the original category is organized in components. And what this condensation does by this vec E is basically it says, okay, any objects that were kind of related by, or sorry, any components that you could have gone to by using an action of this group E are now identified. So it kind of takes your, it's kind of like a way of organizing the components of your category, basically organized by like kind of orbits of the group. And okay, so this is essentially kind of a souped up version of the lemma from before. Is like, what happens if your full category is not just 2 vec, but it was 2 vec sitting inside. This is the best that we can do. We can't say too much about strong diffusion or whatever, but it's kind of, I don't know, it's kind of fun to say something about kind of how the components are kind of organized. Let me give you a very quick example of this one, and this is very nice. You don't need 2 categories for this. You could have done this with just 1 categories. So you could have considered 2 vec Z4, simple objects labeled kind of 0 through 3, simple the fusion is just given by addition mod 4 in the subindex. And what happens is that, okay, inside the Z4, you can consider basically condensing a vec Z2, right? And what happens is that the result of condensing this object, the modules of this, has two components. On the other hand, what you could have done is you could have just, taken two vec Z2 and mod out by this Z2, and this also has two components. So this is a very simple example of kind of what happens. You organize this basically as kind of 0, 1, or sorry, like 0, 2 and like 1, 3, basically. Okay, so great. Okay, this is so much for the theorems, and now we're going to kind of switch gears a little bit. But before I do so, any questions? Okay, great. So going on to the cohomology story. So let me review kind of accounting a little bit. So in general, a theory with only group-like, so like the strongly fusion case, P space-time dimensional objects with Q ambient dimensions to kind of move around in should be classified by some degree P plus Q plus 1 cohomology of EQ, the classifying space, or sorry, like the Qth Eilenberg-MacLane space of E, right? So as Lakshay was saying before, like, what this Q is really telling you is basically saying kind of how many levels of monodality I have, and then P was always just kind of the surface operators that I really cared about. So I could have said this was some sort of Q monoidal like P category. So in the fermionic braided strongly fusion category B, they're classified by something called supercohomology in degree 5. So let's do a quick counting. So you have P here is 2. So Q plus 1 is equal to 3. So Q is also equal to 2 because I want kind of 2 ambient dimensions for these things to go in. So basically, you can think of this case as kind of surfaces moving in 4-dimensional space. So indeed, you can compute this object basically remembering the fact that supercohomology has comes in 3 layers, basically the 0th degree, the 1st degree, and the 2nd degree, given by kind of the first 3 layers of spin bordism of a point. So, and the 3 plus 1D theories associated to this category are condensable to the vacuum if this this thing, which I'll call SW5, is trivial. So what is SW? SW of a point is a spectrum that gives basically fermionic gap theories up to Morita equivalence. Okay, so the way to compute this object is basically with some Atiyah-Hirschsprung spectral sequence. And this is very nice because we know facts about SW bullet of a point. So we just have to compute this object, basically. And this will tell us kind of what is the obstruction to basically condensing this to the vacuum. So in the bosonic case, we want to compute kind of the bosonic version of this SW thing that I showed in the previous page. And we do so by a Galois descent procedure. This was something that Theo actually taught to me. So the way to think about the bosonic case is, let's suppose instead of working bosonically, you treat it as kind of a fermionic theory, but you equip it with an action of the categorified Galois group, right? So this is kind of you take this bosonic theory, you think of it fermionically, but you remember the fact that there's kind of a Z2 symmetry there, which is really, you should think of as -1 to the F. And this Z2 symmetry is really kind of the objects there that are like trivial under the Z2. This Z2F is going to be the bosonic stuff. And the ones that are non-trivial, i.e. have like, not like basically odd fermion number, these are going to be kind of the fermionic objects inside here. And this is kind of, the reason why it's called like the categorified Galois group is in some sense, this is categorifying, something like C over R, like the complex number over the real numbers. There, the Z2 is something like a time reversal symmetry or like a complex conjugation here. This one's a little bit more complicated. It's like we're kind of remembering more information about this thing. That's why I suspended this in degree 1. It's kind of remembering the fact that if you kind of rotate it by 360 degrees, you should pick up a -1 phase because well, we remember fermions basically. So the Galois descent says that the algebra of a bosonic higher category can be considered as basically the algebra of a Z2 1F equivariant higher supercategories. This is just summarizing kind of more mathematically what I just said before. So essentially what we need to compute is we need to compute some sort of twisted SW cohomology. But now we have this Z2F symmetry sitting inside here. So we want to basically converge to this object. And this object I'll define as basically W I plus J of a point. So we want to compute this basically in degree 5 for the bosonic case. So I'll go into some more details about how this computation is done a little bit later. So let's start off with the fermionic case. So remember, we wanted to compute what was the obstruction to taking this strongly fusion, this braided strongly fusion fermionic to category to the vacuum. So start off with basically E is equal to some abelian group, right? 2 to the power of K. And you can basically show that if E had no 2 torsion, this was already trivial. So we're just kind of we're just trying our hardest to find the cases when this cohomology group is potentially non-trivial. So start with the case when it has some level of 2 torsion. So you don't need to follow the details, but essentially the E2 page of the spectral sequence looks as follows. There are D2 differentials given by SQ2 and -1 to the SQ2 1. And so the D2 differential here maps you basically from kind of the second row to the first row, and the D2 differential here maps you from the first row to the 0th row. And essentially, you basically can compute all these HOM and these X objects, and then you just draw the differentials and see what kills. So on the E3 page, after doing these D2 differentials, you find that actually in total degree 5, so just look on the diagonal here, that this guy is equal to 0. Okay, great. So we proved it for the case where E is just this 2 to the K. And then you can say, you can kind of ask yourself if E was a product of groups, product of 2 to the K times like Z2 to the whatever L or something like that, yada yada yada. You can basically show that this is actually non-trivial. So this is like a further computation that we did in this paper. So interestingly enough, if it were just kind of a finite group that looked like this, it's trivial. But if it were a product, then it's non-trivial. Okay, so you know the answer. So we know some sort of answer now, right? Which is like, if the group-like structure of these surfaces was some sort of was let's just say Z2 times Z2, right? Then there would be an obstruction to going further and condensing all the way to 2s vec. So let me do the bosonic case now. So we're going to proceed similarly to how we did it in the fermionic case, but with a couple of modifications. And the details are not so important, but let me just kind of tell you in case you're kind of interested in how these computations work. Is that so? Remember the fact that we had to take into account the Z2F equivariantness. Now we have to upgrade. Instead of the D2 differentials that I showed you in the previous slide, we have to use these twisted D2 differentials. Okay, just twisted slightly by this kind of fundamental class in Z2F. And the group in general is going to be some extension of Z2F, which is kind of the thing that we need to remember for this Galois descent to work, and also E, which is the actual kind of fusion rules of the surface operators. But to see if these bosonic theories could be condensed to the vacuum, let's just forget about this E, right? Because if we put an E on, you can show that basically it makes it more and more complicated. So it's sufficient to just consider, could Z2F have already been condensed, right? And we'll just do the computation with just the Z2F. And we find that basically W5 of a point is non-zero. So these could not have been condensed to the vacuum, just period. Just with Z2F. We don't even need to worry about adding extra complications of the group-like structure of the surfaces. So that's something interesting about the bosonic case as compared to the fermionic case. In the fermionic case, as we said before, you actually have a chance depending on kind of type of work groups that you have. But here it just seems like you can't do it, and the obstruction is this guy sitting in degree 5. Okay, so I've talked a lot about kind of the braided and the braided and syleptic stuff. I did not do the computations for strongly syleptic things, but that was done in a different paper on 5D topological orders, so I won't go through those computations here. But I want to describe some of the symmetric fusion 2 categories. So these are not going to, so as I said in the very beginning, these are not so great as physical theories, but still we can say something kind of mathematically nice about these categories, which I would like to share with everyone. So let me review the one Deligne theorem. So the one Deligne theorem says the following: is that working fermionically, there exists a fibre functor f from rep G into S vec. So what are the implications of this? Suppose you have a 4D or 5D topological order, topological theory. What this means is that you could have condensed all the lines away if you allow for like emergent fermions. Because, in this high dimensions, the lines are just completely symmetric. So notice I said the lines were symmetric, but not everything in the category was symmetric. So that's the important point to remember. But this is kind of nice. It's really saying that if you cared about kind of 4D and 5D theories modeled by some higher categories, you could have just used this this one Deligne theorem to really get rid of the lines very, very quickly. So we want to upgrade this this existence of fibre functor thing for 2 categories. So the point is that we show that every symmetric fusion 2 category emits a fibre 2 functor to 2S vec. Okay, so let me just outline a little bit how we do this. So the strategy is to take a symmetric strongly fusion 2 category S with E, its abelian group of basically connected components. So the idea is basically, okay, so there's something that I said about selected categories and what you could condense inside those. It turns out that as a corollary of one of the theorems before, you could actually show that you could have taken your symmetric category and made it a symmetric strongly fusion. So now what we'll do is we'll look inside, and we begin by describing basically Sx, which is the Picard sub 2 category of this of the strongly fusion 2 category. And then we'll recover this S through some properties of S cross, which is easier to work with. So the Picard 2 subcategory fits into basically the following exact sequence. HE is like some Eilenberg-MacLane spectrum of this group E. And in particular, you could have you could basically you can see that this is completely determined by basically these maps from the spectra HE into the suspension of 2S vec. This is also a spectrum. And the point is that these maps are basically classified by the groups SH7, E4. So the way to count this is basically, okay, so 2 was the braided, 3 is the syleptic, and 4 is the symmetric. And then I want, so I have 4 plus 2 for the surfaces, right? So that gives you 6 plus 1, that gives you 7. So this is the group that really classifies such categories. And this is a computation that can also be done. So we can compute kind of whether this group is trivial or not. So via another spectral sequence, similar to kind of things I showed you before, except just using the super cohomology, which only had degrees 0, 1, and 2, you can show that this is actually equal to 0 for all E, which implies that basically you could have split the previous exact sequence. You could write this thing as a product, as a symmetric monoidal 2 category. So this is very nice, because then now what you can do is tensoring with 2S vec over 2S vec cross, and Karoubi completing this object actually recovers for you this S. This implies that this S initially was just given by 2S vec E for some group E. And using the lemma that we discussed before, this guy is a very nice thing because you could have just condensed out the vec E inside this, and you could have just gone to 2s vec. So great, this basically does exactly what we needed to do. It shows you that you can really condense all these symmetric categories into 2s vec. Let me just mention that the importance of kind of 2s vec was that if you just looked at kind of the bosonic case, so now you just want kind of fibre functors, or I should just say kind of functors into vec instead of s vec, that's not always guaranteed because, you know, just like in kind of Chern-Simons or something like that, if you had fermions, that would be a problem. And indeed, if you computed H7 E4, you would notice that this is non-vanishing if E has two torsions. So this is not automatically 0, unlike this computation that we did in the super case, which was 0. So this shows that this really does generalize kind of generalize the one Deligne theorem very nicely, and also uses the fact that we need to work with fermions as well. Okay, so basically to conclude off this talk, we wanted to, you know, initially take some 2 category and simplify it as much as possible. So we wanted to basically consider modules of this 2 category with respect to some nice algebra object inside. And then the nicest cases we found was if you can kind of look inside and grab a subcategory that looks like 2FG, right? This is the connected case 2FG, but you know, if it was 2VecG, we also saw something nice about how the 2 category got organized, at least the components of it. We found the modules at a purely algebraic level, i.e., you know, we just described to you kind of the properties of the modules with respect to some algebra. And then very nicely, if the category could have been made strongly fusion, we can really compute the obstruction to condensing all this thing, to condensing the whole category to the vacuum. So now, you know, in this case, the obstruction was very manifest, and somehow the anomaly was also like very manifest in these cases. I would like to just say that, you know, it would be very nice to fully generalize one categorical data, such as you know, the data of like modular tensor categories and stuff like that, and really use that in kind of a nice way as we use anion, as we kind of use these data for anion condensation and really apply these to 2 categories. And maybe we can go even further and kind of, you know, say things about the bimodules of this category with respect to some algebra object. And I think that would be really, really cool. But I don't know how to do things like that as of now. And of course, you know, to also go a little bit further and really maybe kind of define anomalies even better than we did here in the case where, you know, we can't fully condense out the category. What is the right object to really talk about the anomaly inside of? And so that's where I'll end the talk. Thanks everyone for your attention.
So thanks, Matt, for this nice talk. Are there any other questions?
Hi, Matt. Sorry I joined late, but I was wondering if you can go back to one of the theorems in the previous slide.
Yeah, sure. So just tell me what this is.
About the fibre functor. I think you have a theorem about.
Did I go too fast?
Yeah, maybe. Yeah, this. Oh wait, I thought there's a theorem saying that every fusion 2 category emits a fibre functor.
Okay. So this is the 2 Deligne. This is the 2 Deligne case, right? Is this the one you wanted?
Yes, exactly. This theorem. So, sorry, I joined late, but can you say a little bit about the physical meaning in terms of gauging and anomalies of this theorem in the context of 2+1D quantum field theory?
In terms of 2+1D quantum field theories, well,
I mentioned that because I thought the surfaces in a 2+1D quantum field theory has something to do with the fusion 2 category. Maybe I'm completely wrong.
So let me describe for you what this is really saying physically, right? So as you probably missed this, but let me just back up a little bit. So consider the number of dimensions I need for surface operators to be fully symmetric. I'll go back to the 2 + 1 case at the end after I describe this.
Oh, I see.
So in order to be fully symmetric, I need enough ambient dimensions in order for this to happen. So I need at least 6.
Oh, I see.
So the context in which this would work is if you have some very, very high category
I see.
in some high dimensions, and you want to ask yourself, what can I do with these surface operators? Kind of like in this example, right? So for line operators in some higher category in high dimensions, using the one Deligne's theorem, I completely get rid of all of these guys, right? This generalizes and says if I'm in high dimensions and high category number, and I just look at the surfaces inside, I can get rid of them in a similar fashion because they become symmetric in this setting, right? So high category number and kind of high dimensions is when I would really use this theorem. So this is kind of going to like topological orders and like very high things.
I see.
So let me just make another remark, which is that, you know, in the classification of kind of 4D, 5D topological orders, what was the most important thing there? It was really the surface operators and the line operators there, right? The 3-dimensional operators and stuff are built of condensations of these guys. So we really just had to consider kind of 1 and 2, basically just 2 categories was enough, right? And the story there is basically use the one Deligne theorem, get rid of all the lines first. Now the category becomes very nice, becomes very group-like, right? And then use some cohomology techniques to really understand this thing. So what this 2 Deligne thing is trying to say is, you know, play the same game, right? Suppose you have kind of membrane operators that are 3-dimensional, and then you have 2-dimensional stuff, and then you have 1-dimensional stuff. Okay, get rid of the 1-dimensional stuff, get rid of the 2-dimensional stuff. Now we need to say things about kind of strongly fusion, like 3 categories or something like that.
I see. So my question didn't make sense because the surfaces in 2 + 1D won't be symmetric, and you say you have to go to say.
But anyways, the surfaces are just going to be condensations of lines, anyways, right? So,
right.
And the lines are not fully symmetric in 2 + 1D. Yes.
Right.
So hopefully that was clear.
Right. Yeah. Thank you. Yeah, that was clear.
Are there any other questions?
Yeah, can you go back to the end of the first part of your talk where you discussed the Z4 example?
Sure. This is actually a
Yes.
really nice example.
The 2 rep Z4 and you gauge the Z2. Yes.
Yeah.
Yes, we also discussed this at length with people. So one question is, so here it wasn't quite sure. So this mod 2 vec Z4, where the algebra object is vec Z2, is 2 connected components. So this is, I think you're saying when you gauge the Z2 inside 2 vec Z4, you get something that is essentially 2 vec Z2 and a 2 rep Z2, right? But then you have some additional data. So one question is whether you actually pinpoint this additional associator data in this. So there's a 2 category that is describing these modules. And the question is, do you know what the full categorical structure is from this? It wasn't clear whether that was not just on the slide or whether you had worked this out.
Okay, so yeah, I don't know the full 2 categorical structure in this case. I never worked out associators or things like that. This is just working at the level of, this is just working at the level of kind of the fusion rules, but not the associator data.
Okay.
You can see this. Yeah, sorry about that.
So you wouldn't see the difference between Z2 and Z4. If you start with the Z4 group, 2 vec Z4 versus 2 vec Z2 times Z2, you wouldn't see the difference.
So there, well, oh, I see. So I think it depends on kind of what you condense in these 2 things. So in the it would like the algebras will look a little bit different in the Z4 or the Z2 times Z2 case. I would have said that in the Z2 times Z2 case, you kind of have to pick the center, or sorry, like the diagonal Z2 here. Whereas the Z2 here, I could have just picked basically I could basically pick the lines like 0 + 2 basically, right? Which is like the Z2.
That's right.
And condense that algebra, which is 0 + 2.
Okay. All right, thanks.
But there it would be kind of like 0, 1 and 0, 1. I need to pick kind of like something here and something there. So that's how I would see it.
Okay, thank you.
Okay, if there are no other questions, let's stop the recording and ask any other unofficial